All right.
And so, great. So with that, Yiannis is going to be talking about robot learning from vision and language. Yiannis, please take it over.
Yeah, thank you. Good afternoon, robotic friends, or I should rather say robotics friends. I come from the Computer Vision Lab, the oldest and largest laboratory of its kind in the world. It was established in 1965 by Arthur Rosenfeld. And we do a lot of our work in the Autonomy, Robotics, and Cognition Laboratory. And I co-direct with Cornelia Vermeulen, the Perception for Robotics group, where we do perception for robots. Because, you know, Google Vision, Facebook Vision, and multimedia vision is not the same as robotic vision. So in our lab, there are basically 3 topics studied with regard to active and interactive perception. That is, the groups of PhD theses are centering around these topics. One is about models of action that I will talk about today. Another is about visual navigation under swap constraints, where we work with very small drones and we use event sensors that my colleague Cornelia Vermeulen will talk about. And the last one is about hyperdimensional computing, because, you know, robots will have to integrate information from different modalities, like vision, sound, control, decision, memory. And for the time being, these disciplines are speaking different languages, and hyperdimensional computing has the chance of unifying all of this so that we can do multimodal learning. So the problem we'll look at today is we observe a human perform an action. So we have visual information. Then we learn a model for that action. And then we perform the action with a robot. So we've been working on this problem using basically grammatical constraints, like you have grammars for language. You also have grammars for action, where basically you form the trees. You form the trees when 2 objects merge whenever they begin or stop co-moving. So you consider contact as the fundamental for making the parse trees. So for example, you see here, somebody's making a sandwich bagel. Now bagel and plate touch. Bagel, plate, boom, you have a little tree here. Hand touches knife, knife. Knife touches cheese, knife, cheese, boom. Now knife touches bagel. So you get those activity trees, or here is an activity tree from an application in the factory. And you can use this to basically parse actions, even if the actions are different. You start one, then you begin another one, then you go back to the previous one, and so on. So here's an example. Let's say this is this person here cutting a vegetable with a knife. Then by having this grammar, which is now more sophisticated than just contacts, you can create this parse trees as the action is evolving. And we have ways of modifying those trees, you know, when actions are finishing. And then having those trees in the grammar, you can turn the activity into a number of commands, like the ones you see here at the bottom. Left hand grasp knife, right hand grasp eggplant, and so on and so forth, that a robot can now execute. So if H is for hand, G is for grasp, O is for object, A is for action, then you see one of the productions here. A plus O gives an action phrase. An action applying to an object is an action phrase. Hand and an action phrase is a hand phrase, and so on. So you can see the development of that grammar. And let's see an example of that. So now the robot will do the action that it observed, okay? So in the interest of time, I will move forward. Here's another example. Now the robot repeats exactly the same actions that have to do with pouring to make a drink, okay? So we have been working on this framework for a few years. We have a problem generalizing to thousands of actions, and we have solved this problem recently with this new theory of the Therblig. Now, Therblig is the word Gilbreth spelled backwards. So Frank and Lillian Gilbreth, about 100 years ago, they were industrial psychologists, and they were very interested to understand what movements are people doing when they work in factories or in whatever kind of job. And so they observed thousands and thousands of workers. They were a couple, by the way, and they were the inspiration. They had 12 children, and they were the inspiration for the movie Cheaper by the Dozen that has been made twice. So basically, the Therblig are a system for analyzing the motions involved in performing a task. And they invented that system and refined it. And of course, the motivation was ergonomics and efficiency. So here is they identified 15, and other authors made them 18. They are like transport loaded, when your hand is moving and holds an object, or transport empty, your hand is moving and it doesn't hold anything, or position an object, or preposition, or assemble, or disassemble, or search when you are looking with your eyes for something, select, and so on and so forth, grasp. Therblig. So here is, I'm sorry for the quality of this, but it's from an old film. A person is picking up this object and it's taking out a very small piece and uncaps it. So it's all done with Therblig. It's from that time. So basically the idea is that you have a small number of Therblig for all actions. And so here, for example, we denote T, transport empty, TL, transport loaded, G, etc. And so, for example, if somebody is making a bowl of cereals and bread with milk for breakfast, the whole activity, you can turn into this Therblig. T, plate, G, plate. Basically, you put now the objects, the nouns, as arguments in this Therblig functions. And so that gives us the ability, if you are also able to understand when the hand is going, so that you can anticipate and predict contacts, something that we have done. You can see here for these videos, you can make contact anticipation maps, and also the next active object, like your hand is moving, is going to some location, and there is an object in that location that you can segment. If you can do that, so basically what you could accomplish is using transformer networks. You can take the video of the action and you can turn it into Therblig, and then you can use basic constraints on the Therblig with another network to produce the actions. Because, for example, if your hand is moving and it's holding something, you cannot grasp something with that hand. Okay, so a consequence of the Therblig is that all actions are basically small programs. Okay, you can see that by having a sequence of Therblig and then parsing it. And so we are developing a programming language that basically represents human action and action in general. Like, for example, this guy is cutting tomatoes and putting them here. You can write this with a small program, okay? And this language basically has the functions are at least the Therblig's. So what we are doing right now is working on these problems where basically we implement 4 different systems: VALC, the Visual Action Language Compiler; VALT, Visual Action Language Debugger; MALC, Motor Action Language Compiler; and VALT. So basically, from an input video, you'll be able, using the VALC compiler, to create the action program that is happening in the video. Then using that action program, you can create an augmented reality system that will guide you through a task, much like the DARPA PTG program that is going on right now. Now, the MALC is the Motor Action Language Compiler. And basically, what you want is you want to write programs for any robot. So writing those programs, you must have now a compiler that will take that program and basically make it a program for your particular robot. And the VALT is the translator, where basically you take video, you translate it to language, and you do that through the intermediate step of the action language program. Okay, thank you.
Thank you so much, Yiannis. And I'll again do the virtual clapping on behalf of the audience here. We do have some questions on the Q&A, and so I'll go ahead and read one. This is from Rahul Karanam. He says, "What is the training time for the robot to perform the task by learning from the action? And then, do we need training data, or all the actions are fixed? Do you consider the sensory details of the actions, like force, reaction angle?"
Yeah, so basically here the idea is that we are learning from one action. You are observing and you are learning, but you are not learning the movement. You are not learning the movement. You are learning the subtasks that are inside that task, okay? If you and I cut a cucumber with a knife, we will not have the same movements, but we will both grasp the knife. Maybe you with your right, me with my left. We will both bring the knife to the cucumber. Maybe by bringing the knife to the cucumber or the cucumber to the knife, we'll have to get them to contact, and then we'll both move, do cutting actions. So the imitation learning problem in the past, it was treated as a problem where they try to learn the exact movement, but that is not important. What is important is to imitate the individual subtasks that are happening, like grasping, cutting, and so on and so forth. So the Therblig's theory that I described is doing this now for free, okay? So to summarize, this is one-shot learning, as it is called in the literature. And basically it assumes that you know several other things. You know how to grasp things, for example, okay? Or you have knowledge of objects. Okay.
Thank you so much.